Vai aparecer lá no alto da tela, streaming, YouTube, lá no alto, à esquerda.
On YouTube, live on YouTube, né? É isso? É. Tem mais gente chegando. Quando for 9 horas pila, a gente começa, né?
Uhum.
Exato.
É mesmo.
É curioso, ainda não começou no YouTube, não, mas...
Você quer que eu espere para começar quando estiver online lá?
É melhor. Já está quase lá, é mais um minutinho, ele demora...
Uhum.
Tem algum sync que ele começa a bufferizar na imagem, e...
Uhum.
que aí pelo menos a gravação fica completa, né?
Uhum.
Ainda está aparecendo só o vídeo do Casanova aqui. Como é que... Cadê o live do departamento? Estranho. Lá está marcando live, né? Manual, já era para estar aparecendo. Strange.
Mas você vai ativar o recording aqui do Zoom?
Não, não. Só do YouTube já é suficiente. Já. Agora, por algum motivo, eu não estou vendo aqui.
O Garantia não quer manter o recording aqui do Zoom, então, cara?
Não, ele tá
Vai entrar?
Alguém pode checar lá no site como é que está? Bom, ontem foi... começou, já está aqui. Já.
Começou? Então, 9 horas.
Quando eu cliquei em vídeos, está aparecendo o Carlos Eduardo, estou vendo aqui ele, mas é sempre um pouquinho atrasado. Né?
Então eu posso começar?
Eu vou pedir para todo mundo, então... Vamos lá, pode começar, então.
Bom, então, bom dia a todos. É um grande prazer receber todos aqui nesse tutorial 2 do SBBD 2020, organizado aí pelo professor Sérgio Lifshitz da PUC. Hoje é uma grande satisfação receber o professor Patrick Valduriez, que já tem um histórico longo de colaboração aqui com o Brasil. A gente pode conversar aqui nessa parte introdutória em português, porque ele entende. O Patrick, eu fui caçar a história de colaboração dele com o Brasil. Ele participou do primeiro SBBD em 86, que foi, por incrível que pareça, no Copacabana Palace, organizado pelo Rubens Melo. Também, em 94, participou de um workshop a caminho do VLDB no Chile. A Rosana Lancelotti e a Esther Pacitti organizaram um workshop e vários dos pesquisadores da época, inclusive o Patrick e o Henrique Simon do IRA, vieram para esse workshop. E, desde lá, foram várias orientações de alunos do Brasil, a Rosana Lancelotti sendo a primeira, seguida pela Esther Pacitti. Em seguida, fui eu mesmo, e o Sérgio também, naquela época, estava no IRIA, e aí seguiram-se vários alunos de doutorado, mostrando assim o interesse, né, e a contribuição do Patrick com a comunidade brasileira. E é claro que o Patrick é conhecido pelo livro dele, né, o Principles of Distributed Database Systems. Qualquer um que tenha estudado aquele segundo curso de banco de dados passou por alguma das 4 edições do livro do Patrick, né? Então ele está agora na 4ª edição, e que traz esse novo assunto, o New SQL, além de outros assuntos, mas ele vai abordar na palestra aqui o assunto New SQL. Eu estou vendo a Marta aqui, que é uma colaboradora também forte aqui do Patrick. E, bom, os slides do Patrick, eu queria dizer, vão estar disponíveis na página dele, então vocês não precisam se preocupar, é só procurar Patrick Valduriez, cair na página dele que os slides vão estar lá. E queria dizer que assim, essa colaboração assim, que é contínua e mostra o interesse dele no Brasil, gerou, por exemplo, a construção, o estabelecimento, está em curso de estabelecimento do INRIA, Laboratório Internacional do INRIA, aqui no Brasil, né? Então, isso demonstra um commitment do INRIA, né, com a pesquisa em computação no Brasil. Então, sem perder mais tempo, eu passo o stage para o Patrick. Patrick, por favor, obrigado mais uma vez por aceitar e gentilmente compartilhar a sua palestra aqui com a comunidade brasileira.
Obrigado, Fábio. Bom dia a todos no Brasil. Hello, everybody, since many people will not understand Portuguese. Obrigado a Fábio e Sérgio pelo convite. Estou muito feliz por fazer este tutorial na SBBD, porque o público brasileiro é muito simpático e muito bom. Mas eu teria preferido fazê-lo fisicamente no Brasil. Talvez a próxima vez vai ser melhor. Agora vou mudar para inglês. Now let me switch to English. Let me share screen. And then okay. So I guess you all see, so as Fabio said, all the slides will be available on my webpage. Just enter Patrick Valduriez on Google, you will find it easily. So you all know the title of the talk, which is a spotlight on NewSQL, but I will talk also on principles of distributed database systems. You will see why my affiliation is also with Linscale later on. I'll explain that. So the outline is, I say a few words about distributed database systems and the new edition of the book that Fabio mentioned. So the book introduces a lot of new stuff compared to the previous editions. So I will briefly mention some, like NoSQL, Polystore, and this will allow me to zoom on NewSQL. And if there is enough time, I will end up with a taxonomy of NewSQL systems and discuss current trends. So the first part I want to, the first part I want to discuss is principles of distributed database systems. So based on the 4th edition of this now classic book with Professor Tamarozu, that just went out at the beginning of this year. So why is that? Okay. So let me start with the story of the book. It's a long story, but most of all, it's a friendship story. So Tamer and I, we first met when we were PhD students in the summer of 1980. So 6 years before SBBD in Copacabana Hotel. So that's 40 years ago. So we met at Ohio State University while we were PhD students. Tamarozu was there. Then what happens is a very important point in time is in 1986, we were at the Hawaii International Conference on System Science. And we had a cool meeting at the hotel swimming pool. And I guess we had a long discussion with Tamer and we decided we should write a book. So here it is. So I have a problem with switching. Sorry. Okay. So the first edition of the book started in 1991. So that's 5 years later. It took a while because it was the first edition. The focus was on relational databases, which was maybe beginning at that time. Very interesting, there's a quote that we have in the preface from Michael Stonebreaker, who said that in the following 10 years, centralized database management system would be an anti-curiosity. And in fact, today, I guess, this vision has been realized since most organizations use distributed systems. Oops. 1999 is the second edition. So as you can see, there are translations in both Spanish and Portuguese, Brazilian Portuguese. So this edition brings new stuff on advanced transaction models, query optimizations. These were very hot topics at the time, object data management and parallel database management systems. 2011, third edition. There's a Chinese translation. So then we, of course, each time we revise the previous chapters because so much happened between the two editions. And we added data replication, database clusters, web, data integration, peer-to-peer, and cloud. And 2020, so the last edition, basically we got rid of many chapters which were there in the first edition because we also introduced basic technology, which is now well known. And so we made room to introduce the new stuff like blockchain in the peer-to-peer chapter, big data, data streaming, graph data analytics, NoSQL, new SQL, and polystores. So I will briefly mention some of this stuff. By the way, I will not talk about blockchain at all because there's a very nice tutorial, I think, by my friend and colleague Amer El Abadi, who gave a very good tutorial on the topic last year at in our French National Database Conference, which is the equivalent of this one. So very interesting. I like this slide very much because it was in the first slides of the first edition. It's a distributed database user view. So basically, each point in this picture is piece of data, and all the users can have access to this data independent on how it is implemented or distributed. Well, if you look at the user view in 2020, well, it's basically the same, right? Except that everything is in the cloud now. And maybe the computers that access them are different. Well, what has changed between these two editions is that the number of users is much higher, and the number of machines that are behind the scene is much bigger as well. So essentially a problem of scaling. So the reality, as you know, is that behind the scene, well, the important point is the data is located. It has to be located at some point at some nodes in the distributed system, which can be data centers today, or it can be nodes in a cluster within the data center. And this is very complicated, in particular because some data might be also replicated in other places for various reasons. So I start very basic. So a distributed database is just a collection of these multiple logically interrelated databases, and they are distributed over a computer network. In the first edition, we were focusing on wide area networks. And then I think the second edition, we added local area networks. And of course, today, another major type of computer network is cluster interconnect, where you can have thousands of machines in the same room or in the same building. So the distributed database system is just the software that manages the distributed database and makes all this distribution and implementation transparent to the user. So it hides complexity. Oops. So this is very important because based on this definition, we can have what I call promises. The promises were there from the very beginning of the definition, and it took maybe like 30 years to start to be feasible, in particular because of new technology that I will be talking about, which can deal with scalability. So, of course, the first important point is transparent management of distributed, fragmented, or partition, if you want, replicated data. And I think a major result is declarative query languages, in particular SQL, which is really the standard language. So there have been a lot of debate about whether SQL is good or bad, but it's really a fact of life. It's going to be there for a while. By using replication and advanced transaction model, you can have improved reliability and availability. So an important point that SQL systems provide is a strong ACID consistency, as well as failover online recovery, so that you can have applications that run 24-hour a day, 7 days a week, all over the world. A very important point, aspect is performance. So in distributed systems, in particular in databases, we want to avoid moving the data because it takes time. So there is proximity of data to where it's used, but you can also use the fact that there are many machines. And this is what we call data-based parallelism. And of course, query optimization, which is related to the fact that we have a declarative query language and you have a very complex execution system. So it makes the query optimization problem very complicated. And a very important aspect, the final one, is the easier and more economical system expansion compared to a centralized system. And just in the cloud, this is what's been called now elasticity. So you all know about the advantage. So an important, so this is from the first edition. I'm sure Tamer will be watching maybe later on because it's very early right now in Waterloo. But I love this slide. This is a slide that Tamer came up with to understand the various dimensions. You can have many more dimensions, but there are 3 basic dimensions for what we are talking about. Of course, distribution, number of machines, number of sites, heterogeneity, the fact that databases can be in different data models, they can use different languages, and autonomy, which means the way the local databases are controlled. So they can be controlled centrally or fully distributed. And what's very interesting is that even in the 4th edition, we are able to have all the new technology. For example, NoSQL and USQL will be here, meaning that they don't have any autonomy and heterogeneity, but they have high distribution. Peer-to-peer would be here because of autonomy and distribution, but no heterogeneity. And we'll talk about Polystore, and you can view them as similar in a way to multi-database systems, which have both distribution, autonomy, and heterogeneity. Okay, so an important aspect when I talk about the dimension, the distribution dimension, when you have lots of components, a lot of machines, is is speed up and scale up. So I'll start by defining speed up, which is there from. So it's an objective, and the ideal is linear speed up, which is basically a line like this one, which says that if you increase the number of components, number of machines, number of disks or whatever, and the network, and you keep the database size and the workload fixed, this is very important, then you will grow, you will have better performance. So for example, if you double your configuration, you should divide by 2 the response time of your analytical queries. Okay, this is very hard to achieve, especially that in practice, it's more like, you know, it starts growing and then at some point it starts going down. And why is that? Well, it's something well known. These are called the speed up limits. So there are limits which are based on the infrastructure, so basically hardware and software. So we all know that if we add more resources which are shared, arbitration conflicts will increase. So for example, if you have a multiprocessor machine, access to the bus by processors, which gets faster and faster every year, will become a problem. Another example is latching. But here, I guess we cannot do much about that, except that it has a big impact on the kind of distributed architecture, share nothing versus share disk, we'll discuss later on. But where we can contribute is dealing with the application. And we all know that only part of an application program, SQL query, for example, can be parallelized. And this is based on the famous Amdahl's law, which gives a maximum speed up. I love this law because it's very simple and it's very accurate. So if I call sec the fraction, percentage of code that cannot be parallelized, then this will give me the maximum speed up that can be achieved based on the number of processes. So obviously, if sec is 0, I can have full parallelism. With 4 processes, I will get a speed up of 4. I cannot do better than that, okay? Now, if I have only a third of the application, which is sequential, like 30%, with the same number of processes, the speed up is almost divided by 2, which is very serious. And usually when people had this kind of problems, they say, well, it's not a big deal, we'll just add more machines. Well, what if I add 4 more nodes? Well, as you can see, the speed up is only going from 2.1 to 2.5, which is not much. And in fact, it will, I will need lots of processes to go close to 3, which is very small speed up, okay? So it really means we need to work on this sequential part and make sure that we have a way to parallelize queries, or in the case of big data, to have frameworks like Spark, which allow me to deal with this part. Okay, so in other words, you cannot think in terms of sequential processing, otherwise it's going to be a very hard problem. Okay, a more subtle measurement is scalability. So here I'm defining scalability as in the book. In industries, and this is a big discussion with Linscale, we have a slightly different ways of going to scalability, but I will stay with this for the moment. So the ideal is to have linear scalability, linear scale up, which means if instead of just increasing the components in my system, the nodes, the network, I also increase the database size and the load, I want to keep the same performance, okay? And that's very important if you want to have a long-term view of your application. Think of a search engine, right? The first search engines, they had very small data, very few users. And now they have millions or billions of users. And basically the response time of a search engine query is still about 2 to 3 seconds, right? So this is very hard to achieve. And in fact, it has a big impact on the architectures. So a bit of terminology, you will often find vertical, horizontal, scale out terms and so on. So what does this mean? Well, it basically means that, well, it refers to computer cluster architecture. So basically you have nodes, like P1 is processor, memory, maybe some disk, and you can put these nodes in a cabinet. So you can put maybe like up to 40 nodes like this. So by adding more nodes, you make the cabinet or the machine more powerful, and this is called scale up. So a nice way to look at it is because of this vertical way of organizing the machines. But it can be organized differently, but it's just scale out is very interesting. It means that when the machine starts to be full and you cannot increase its capacity except by going to a bigger machine, you can do scale out. And scale out is just simply by adding another machine, and you interconnect the machine with the previous one, and so on and so on. And this is called scale out, and this is typically what a computer cluster provides. Okay, and all the cloud providers, they use this kind of architecture because it can scale to very well. We don't know today what are the limits. The limits are probably in terms of energy consumption, cooling, and stuff like that. So it's more hardware based. Okay, so how do we deal with this issue that the Amdahl law tells us that it's hard to do? Well, we need to make sure that we exploit as much as possible parallelism by being clever. So unlike in, for example, high performance computing, where they use, I would say, low-level libraries like MPI, where the programmer has to deal with parallelism, in our case, remember, we assume a query language like SQL or something like this. So we have a good abstraction and we can represent queries. Like, for example, if I have multiple queries which access, oops, I'm sorry, it should be the same R, I need to correct. Accessing the same data or different pieces of data, they can be run in parallel on different nodes, right? So think of a search engine which is implemented with a distributed database. It will run lots of small queries in parallel, okay? So this kind of parallelism is relatively easy to achieve because you just need some good load balancing technique. Well, if now the queries are complex, so they can have many operations, maybe not 3, maybe tens or hundreds, like the BI queries. What we can do is intra-query within operators. So we can have different operations of the same query on different data. So for example, the select on R can be done in parallel to the select of S. This join can start as soon as there is some data coming in. This is called pipeline parallelism. And now we can have intra-input operator. Think of an operator like the select on a table, which is very, very big. Well, no, this one, S. You can split S into fragments or partitions, and you can do the same select. It's called sometimes SIMD, single instruction, multiple data paradigm, and you will be able to speed up the query. So in practice, the query processor should deal with all these combinations of parallelism. Okay, another point is the what happened over the last, say, 20 years is the this new computing hierarchy. So basically, we are able to build very big, powerful machines, data centers, out of smaller machines. So you start with, for example, a multi-core today, a multi-core processor. So already it's like a multi-processor, but it's fully integrated with memory. Forget about this for the moment. You can attach it to disk. And that's a basic component. And then you can combine many of these, maybe tens of these, into an architecture called NUMA, which is the dominant model now, called non-uniform memory architecture, where all these components will communicate through memory. It's non-uniform, of course, because the access to the local memory is usually much faster than the access to another processor memory. And this is why this doesn't go beyond tens of processors, depending on. But this is very expensive to do because there's complex hardware behind it. And we also have these massively parallel architectures, called also clusters, where you have the same components, but in a fully distributed architecture. So essentially, these nodes, they communicate with other nodes. So within a node, you can have the same communication as here, but across nodes, you have message-based communication, like in TCP/IP networks. And this can go to thousands, hundreds of thousands of nodes. So basically a lot of scalability and a lot of parallelism out of this architecture. Okay, so based on this, what are the main architectures for distributed databases? Well, basically there are two. So the first one is what's called shared disk architecture. So shared disk architecture is basically you have a bunch of database servers with all the technology you find in a database server, like query engine, transaction engine, and so on. I'm assuming that you have something like an SQL API, and the clients, they have user interface, business intelligence, all kinds of applications. So very, very clever over there. SQL API, which makes it very easy to access the database servers. Full distribution of the database servers, so across multiple nodes, or it can be different sites, but the data is shared. And how is this done? Well, typically using SAN, so storage area network kind of technology, which allows any server to access any parts of the disk, okay? And so this has been a dominant architecture for SQL database servers for a simple reason is that it's easy to manage in the sense that it's very easy to add new data and it makes transaction management relatively simple because you can have shared data structures in the shared disk. The negative point of this architecture is that it doesn't scale to high end because of this known cache coherency problem. Like if you have different database servers accessing the same data, the data will be in the database server memory. If there are conflicting accesses, write accesses, you need something which is like a distributed lock manager. And this is very hard to make it scalable. And of course, you need storage and area network technology, which is really complex and maybe costly. So this architecture is still be around and is very good for online transaction processing, okay? So all the big players like Oracle, Microsoft, IBM, and so on, they have a shared disk architecture for online transaction processing, okay? But you also have the share nothing architecture, which is really a fully distributed architecture. And for example, now in the context of NoSQL, people will say distributed architecture, usually by contrast to the previous architecture, the share disk, which, as you could see, is also distributed. But so here's the big difference: is each database server, each node, has its own data store. So that's a major difference. Is the data store is now split into multiple data stores. So we have what we call in our first edition of the book a fully distributed database. Okay, and so the big advantage is you get scalability, and the cost is really good because you can have optimal combination of components locally using a commodity hardware. The only negative point is now if you have a transaction that spans multiple data stores, you need to deal with distributed updates. And as we show in the book, you need to do something like two-phase commit. Distributed protocols are very complicated and they're hard to deal with. So in practice, this architecture is a perfect match for, of course, online analytical processing. So all the big players, well, except Oracle, have this kind of architecture for analytical processing, and also for big data. This is really the standard architecture for big data. And the main reason is that big data applications are read intensive. Okay. Okay, so this is the background that I needed to recall from the previous edition of the book to move to the new stuff. Okay, so now a few words about NoSQL, which stands normally for not only SQL. Okay. So the first question you might want to ask is, well, why NoSQL? Because SQL has been there and so on. So when I talked to Tamer and telling him about this talk, he sent me this cartoon, which is really good. So it shows, well, for example, you need to write a CV and you don't have any expertise in SQL. So basically you don't know anything about the stuff I just discussed. Well, you can put expert in NoSQL. That would probably attract some interest. Okay, more seriously, why is NoSQL important? Well, because there are maybe three major trends that. So the first one, obviously, is the big data. So I'm not going to talk about big data too much because it's now well known. But when people talk about big data, they usually also mean unstructured data, you know, the kind of data you get from the web or from all kinds of devices. The data on the web is very interconnected. So you have hyperlinks, tags, blogs, etc., which is very hard to capture. I think Fabio gave a talk about this tutorial on this, you know. So RDF and all this has to deal with data interconnection. This is also very important. But also, and by the way, a lot of NoSQL systems are able to do RDF and SparkQL processing. And the major aspect is high scalability. Of course, in terms of data, but also in terms of data rates. So you will know that in the big data dimensions, one is velocity, which means that the data can enter your system at a very high speed. And also you may have concurrent users that may or not do updates, but they are concurrent in the sense that they compete to access data and resources. So there are limitations in traditional SQL systems. So in fact, relational database management systems is that these systems are very good, but they are really complex. And in fact, you can find even very good books on database tuning, because tuning is really an art, more than a science. So you need skilled DBAs. you need database tuning, and also in SQL system, you assume the data is really well-defined. So you have well-defined schemas, which is not the case in the big data where you have unstructured data. SQL has become a very complex language with lots of goodies. The last one being temporal extensions in SQL 2011. And based on what I said on the architectures, it's very hard to make updates scalable. And this is why parallel relational database management systems, they typically resort to a shared disk architecture for OLTP, right? And shared disk is hard to scale. Okay, so what is NoSQL? So I'm going to give a definition here. Well, it's very hard because, you know, it's very easy to define an SQL system because SQL is a standard language, and even the relational model is a very simple data model, which is not the case here. So our definition is that it's the database management system which is specialized, specific. So it's good trade-off between performance and whatever. Typically for web-based data, but not only. So it has a specialized data model. So I will focus more on the first one, which is key value, because it's very simple and general, but you can have tables, documents, graphs. And the main idea is that is to make it simple compared to relational, and trade the relational database system properties like full SQL, ACID transactions, data independence for simplicity. So typically, for example, the key value based system, they don't even have a concept of a schema, and they can provide a basic key value put get API. That's it. But then you can gain into horizontal scalability using a shared nothing architecture, of course, and performance. And also, this used to be called the impedance mismatch of relational databases with programming languages. There can be much more flexibility for the programmer here. So the basic API can be fully integrated with a programming language as a programming language API. Okay, a few words about the NoSQL approaches, and I will just zoom on the architecture. So in the book, we defined 5 categories by increasing order of complexity of the data model. So we start with key value, systems like DynamoDB from Amazon, RockDB from Facebook, Redis, tabular systems like Edge-based Bigtable from Google or Cassandra, document NoSQL system, typically JSON based now, like MongoDB, Couchbase, CouchDB, etc. Graph databases like Neo4j, Allegro Graph, etc. And you can also find multi-model which combine, for example, graph and document, which is the case of OrientDB or ArangoDB. So this includes only systems that are really highly scalable. So when because sometimes, and even on Wikipedia, you would find in NoSQL, everything which is not SQL, which I think is a big mistake. So you would find object database management systems, XML database management systems. Remember, for those who've been around for a while, at some point, all these database management systems were supposed to replace relational database management systems. They completely failed. And the only one reason, lack of scalability. So they are not part of NoSQL because they were there much before, and they don't have any notion of horizontal scalability, okay? So I guess now nobody talks about them, or some of them which had scale-out capabilities, they became document systems. Well, the XML or well, some object database management system became a graph NoSQL. Okay, so the key value store distributed architecture is fully distributed. That's a very important aspect. And compared to the share nothing architectures that we seen before, there's still a major difference. So, well, obviously the API is different. It's much simpler. So it's a key value based API. So the functionality is not as big as what you find in SQL. But you have a separation between the key value data store, the key value store with the capability of, say, query engine, transaction management, and also the data storage. And so like, for example, all the key value stores today are able to store data in different data stores. And this is very important because in Hadoop, for example, you may have HDFS, which is really a good way to store unstructured data. In data lakes, you have also unstructured data. So there's some independence of between the way data is processed and the way data is stored. That's a major difference with the traditional SQL DBMS architecture. Okay, so I'm not going to go into the details, but you have some major systems here with the major providers or vendors and some comments. The major comments is that not many of them provide ACID transactions. And this is typically the way, well, you have some ACID transaction in some documents, data NoSQL systems, because if you want to update, well, a full document, which is composed of many objects, it has to be somehow ACID. But this is really an issue that NoSQL is not very good at transaction support, unlike the relational SQL system on shared disk. Okay. Okay, the last thing I want to talk, and then we can have questions before the break, is polystores. Well, the polystore is basically a consequence of the fact that today we have data that is stored in, of course, SQL, but NoSQL, and there are many different kinds of NoSQL, and also big data systems like HDFS. So the main idea of a polystore is to be able to have queries over multiple data stores using wrappers. Okay. So there's a very interesting article in Michael Stonebreaker's blog called "The Case for Polystores," where basically he explains that it's going to be the next big thing, and it's true in a way, because the fact that you don't have a standard NoSQL data model, you have many different systems. In practice, when people want to develop very complex applications, they have to deal with multiple CLAD data stores. So they have to access those data stores, and the polystores, which are also called multi-stores at the beginning, they provide integrated access like a distributed database. Okay, and the main use case for polystores is basically integrating structured data from relational database with big data, for example, in HDFS or in a document database. So it has become a major area of research and development, in particular in my group here at INRIA. And it's still a very hot research topic. It's not as what we used to call federated databases. There are many differences. So for example, in multi-database systems, especially those that we dealt with in the first edition of the book, we have a few databases like corporate databases, maybe less than 10, and the focus is on dealing with powerful queries, updates, and transactions. On the other hand, we also have the web data integration systems like price comparators. They can access many data sources on the web. And the data sources are databases or files, which are behind a web server. But basically, it's for simple queries. So here it's for complex, powerful queries, simple queries. Well, in the cloud, if you want to access multiple data stores, you have more opportunities for an efficient architecture. For example, in the mediator wrapper architecture, you can install the various components whenever you think it's better in terms of performance. So let me give you a few words about, so there's a very nice paper with one of my former PhD students, Carlina, which does a state-of-the-art on polystores. And we divide polystores based on the kind of coupling with the underlying data stores. In fact, we found out that there are maybe 3 kinds of coupling: loosely, tightly, and hybrid, which is a combination of the 2. So I'm just saying a few words. So loosely coupled systems, they are very much like the multi-database system. So it's basically a mediator wrapper architecture. So they are very good to deal with autonomous data stores, because that's the goal of multi-database system in the first place. So essentially there's one, this is very important, one common interface, one single API to all data stores. So if a data store wants to be accessed through the polystore, it has to provide a driver for this API. So basically, the driver has to translate this common interface to the local API, which might be anything like SQL, NoSQL, whatever. So examples are Big Integrator, Forward, and QX at HP Labs. Not going into the details. Tightly coupled polystore. These are very important, especially because they are major products. The idea is to use the local interface of the data stores with a single query language, typically SQL. And you allow data movement across data stores. So basically, it allows you to extend, say, an SQL system to access external or remote tables. And this uses techniques like materialized views and indices and so on. So I guess the most famous example is Polybase from, it was done by Dave Dewitt at Microsoft Madison, and it's been integrated in Microsoft Parallel Data Warehouse to access HDFS data, okay? But there are other very interesting prototypes like Hadoop DB at Yale or Estocada at INRIA in Paris. And the last one is hybrid polystore. So the 2 previous ones they have obvious trade-offs. Here the goal is to have a more control trade-off between data source autonomy, as in loosely coupled system, but also we want to exploit the local data source interface, which is what the tightly coupled systems do. I'll give you an example next, but example of system are Spark SQL, which is a major product on top of Spark, which has been done by Databricks and UC Berkeley. Big Dog, which is the system done by Mike Stonebreaker and people at MIT. And also Cloud MDSQL, which is something done in my team with Linscale. So let me illustrate with Cloud MDSQL what you can do in a hybrid system. That's really something very interesting. So this is based on a SIGMOD paper, recent SIGMOD paper with all these people. So this is a query in Cloud MTSQL, which integrates data from relational database and from a document database. So for example, MongoDB. We've used MongoDB, HDFS, etc. This is MongoDB. But here, so this is a query plan. So it's traditional relational query plan in terms of relational operator, except that here you have this operator called N, which means a native subquery. So what is this? Well, in fact, the MongoDB query is not expressed in SQL. It is directly expressed as a MongoDB query, db.b.find, whatever. And so, of course, you need a MongoDB expert to write that query. But as you can see, in the cloud, in the Polystore organization, you will have this kind of experts, and it allows you to take full power of the local interface. So think of, instead of MongoDB, I have a graph database. If I have a graph database, I want to do best first search operation. Of course, you can write depth first search or whatever in SQL, but it gets really cumbersome and it's just impossible for a query processor to optimize it. In our case, you just write a best first search in, say, Neo4j. Okay, so that's what, and that's why now there is this issue of polyglot systems and polyglot query languages. Okay. So this gives you some comparisons in terms of functionality of these different systems, but I'm not going to go into the details. And in terms of implementation, and then I'm going to stop here, so that I guess we can have time for questions.
Thank you, Patrick. Thank you very much for this very nice coverage of the distributed system, data systems architecture. So we have a couple of questions here. So let me just, so I will start with, there was a question by Marta, and she would like to present it first, so I'll unmute her. So Marta, please, you can, yeah. You can, yeah, you can turn on your video, yeah. Mm-hmm.
Okay, thank you, Patrick, for the great tutorial, and thank you even better for your book, which helps me a lot in my distributed and parallel database courses. And since you keep updating it, I don't have to do anything. Even the slides are there. So that's a great contribution for the whole community. And as for the hot topics from today, I would like to know your vision about some future as we get even more specialized, both in hardware and software. I have two questions. One is, do you see a possibility of the comeback of the database machines from the 80s? And the other question is, since systems are going to specialized hardware, Polystores would have to distribute executions on GPU machines, cloud machines, and other types of machines. Do you think Polystores are really the way, or the only way, or the best way to go for these different CPUs, GPUs, and whatever? Thank you.
Thank you, Marta. So these are very good questions, and in fact, they are hard questions. With respect to, and you're correct, the this database machine was in the beginning of the parallel systems. People tried to do a specialized hardware for database management, and it was not really cost effective. It was very efficient, but it was very costly, and basically parallel systems were built out of conventional hardware except that there's still, I consider Teradata as a database machine because the network is really proprietary. But today you may say that InfiniBand is really like Teradata, except that Teradata's network is more intelligent. But today, you're right, it's getting very complicated. There are new kinds of memories, the new memory hierarchy, processors, multi-core CPU, GPUs, depending on the applications. And now a lot of applications deal with, as we do in our joint work, with machine learning and AI. And also there are many capabilities. So it's something that we, in fact, we addressed in some project with my colleague from Linscale, exploiting new hardware. So in the book, for example, we discuss with Tamer as you know, I did my PhD thesis a long time ago on parallel join algorithms. And today there's, because it's the hardest thing to do is to combine data, right? So a lot of people are still working on join algorithms, but using new hardware. And it's very interesting because if you look at the chapter on the topic, because algorithms that were considered inefficient with some hardware are now like sort, merge, join, and whatever compared to hashing can be better using multi-core. So this is an issue, how to exploit the new hardware continuously. Another issue is that some capabilities, I mentioned shared disk before, and so now there's, I forgot the term, it's in my book, but using software on InfiniBand or networks like this, you can access directly from one node the other node's memory. Okay, so it's like the NUMA architecture, except that it's in software. So this has a lot of potential as well. So my feeling is that it will, like we have NoSQL. NoSQL is different system for different kind of applications, I would say. Then you will have variations with different hardwares for different applications, depending on the kind of trade-offs. Because, you know, when we deal with software, you have you're comparing two, like we do with the students, right? We're comparing two implementations on the same hardware. We have a lot of trade-offs, but now if you have different hardwares, which are optimized, like if you compare machine learning on, say, NVIDIA machines, NVIDIA is doing HPC machines now for AI, compared to, then there's no trade-off anymore because hardware gives you the absolute performance. It's not relative. So it's getting very complicated. So my feeling is that we will have more and more specialized. So it's like, as you say, it will be like database machines. So maybe the same software from a user point of view with different implementation for different hardware. In fact, it's like if you go to Spark, Databricks has different distributions depending on the hardware target. So for example, the specific distribution for GPUs for their machine learning libraries. So now whether, so all this will make heterogeneity much worse. So if you look at the 3D picture at the beginning, then there will be room for other kind of systems. So I was not thinking about polystores, but yeah, I do believe that polystores is good because you can have a combination of loose coupling or tight coupling depending on the trade-offs. So definitely is probably the way to go, as opposed to grab everything and to copy in another system, which might be an alternative. But I think polystores will be able to deal with this kind of heterogeneity. But now the main issue will be how do you deal with big data? If you have to access big data, you have to be able to exploit. That's why I like Cloud MDSQL a lot because I think it's probably the only system that if you have to access, for example, billions of rows in a system, if the system has a local interface that allows you to select 2 rows, you will access only 2 rows. Whereas it's with the others, because of the translation and so on, you might end up accessing much more data. So it's really an interesting topic. Maybe it's a long answer, but it's a very important question. So thank you for sharing. I can take a couple of others. Yeah.
Maybe I can hook up on this Marta's question. And so I think one of the problems in this context is that when data increases, the amount of data becomes really big, the traditional approach is to partition the data. You mentioned that in shared nothing architecture and so on. But partition itself is a hard problem. And mostly because, you know, the well-known algorithms are based on static workloads. So you take Schism, for instance, which is that graph partitioning algorithm. You have to know in advance the workload expected over that data. On the other hand side, processors are getting increasingly more powerful. So if you take Cerebra, for instance, it's a processor now for AI that has 400,000 cores. So how can we actually build query strategies that can actually, on one hand side, deal with the problem of how to best partition your data, considering that queries usually are not known in advance. The workload is something that you may learn, but you do not know in advance. But on the other hand side, you have processors with 400,000 cores. So that should be its usage should be maximized. So what is the tendency or the perspective of query processing in that context?
I forgot the name, but so there was, I forgot the name of Stavros, I forgot his last name, a guy who did his PhD at CWI on,
yeah. Stavros, yeah.
He was Stavros. He's at Harvard now. And he's dealing with this issue, as you say, well, partitioning or indexing in more generally, takes a lot of time and you need to know things in advance. And his approach is that you start with nothing, and as the queries come, you just build, you start building indices. And I think you can extend this to partitioning. So it's basically learning with the workload. So so initially you're not very efficient because you don't know the queries, but the more you know so of course there needs to be some stability in the workload, right? Every query is completely different than the previous one. You will never, but it's simply simple as in machine learning. So, and I think he's still working on this area. This is very promising. And it's really a completely new way of thinking about things. So I think your question is very good, and Marta's question as well, is that, you know, I remember the first workshop on database machines in Syracuse, organized by Syracuse University in New York State. And I had discussion, I was more a software person, I had discussion with hardware people, and I was doing query processing, and there was, the question they were asking is, why do you bother, you know, spending all your time doing query processing? Just use hardware to do things and to be clever. So maybe now it's time to go back to, it would be nice to go back to those ideas at that time, you know. Yeah.
Okay, thank you, Patrick. So there is a question here by Sergio. So I will unmute. Actually, Sergio, you can unmute yourself. Just go ahead. Sergio? Yes.
I'm not hearing you.
Now I can.
Yes.
Sorry. So nice talk so far, Patrick. Thanks for accepting to come virtually to SBBD. As Marta said, it's a pleasure to have you around us, with us, so many friends, Brazilian friends. And also thanks for your book. It's very helpful. And the last version is very good too. Anyway, I just have a simple question. It's a more philosophical question too. Are these restrictions on NoSQL and SQL questions are mostly technological ones, or are fundamental scientific ones?
I think I will elaborate on the answer in the next part on new SQL, but I think there are basic limitations in the ways they've been designed. So I believe there are inherent limitations. Okay, and it's very interesting because SQL systems in a way, because SQL has been designed for initially for OLAP applications and then OLTP. This was very interesting, by the way, because the first version of SQL systems, they were not good at transactions, and we had to wait for Sybase to come on the market to do stored procedures and whatever. And but today, everybody understands they can do both workloads, and with NoSQL, they're really specialized for specific workloads, and so in a way they get limited. So this will be the topic of this is why we have NoSQL, in fact. But in their niche markets, they are very good. For example, if you want to manipulate JSON documents, or if you want to do graph, well, with graph, I'm not so sure, because you may want to store your graph in a relational database and you use the graph frameworks like Giraffe to do complex graph processing. So that's also another issue. But it's always a problem to have a system that is very limited to begin with, because it will be hard to evolve. Okay. And if you look at all the success stories, so the biggest success story today in terms of SQL system is Snowflake. You've heard of Snowflake. So Fabio knows the story because Snowflake has been, so it's a company that is now worth $30 billion. And it's been done by one of my ex-PhD students, Benoit Dacheville, who used to be at INRIA. I think Fabio missed him, but maybe Sergio, you remember, he was at Bull with me at that time. And Snowflake, well, it's basically a relational data warehouse, but the big difference is that it's in the cloud. And so it shows that, well, at least customers, you know, they're really okay with really powerful database technology, okay? And I've not heard of any success story like this for NoSQL, okay? Okay, is it time for the break? How do you want to, or do you want to take more questions?
There is one more question by Javan, so we could take this last one. Then we would have 5 minutes before continuing.
Okay,
if you want to drink some water.
Yeah, yeah.
Let's just unmute Javan.
So who's going to ask the question?
Javan, just, okay, so you are unmuted now, Javan. Go ahead, please.
Hi, Patrick. How are you doing?
Hi, Javan.
Hello. I just have a very simple question about the sharing of metadata, because, you know, these days we're also sharing, I mean, I'm talking about the data processing in a distributed manner. And the last years, we have a lot of data about the data. And then I'm just wondering if you have any clue, or what do you think of a nice way of also, when you distribute the query and you need to, share data between nodes in a distributed database system, what is a nice way of also sharing and distributing the metadata or the data about the data, the constraints and everything? What do you think?
Well, the simplest way, it's a good question. The metadata is important. So it depends what you talk about. If you just talk about the metadata on the data in the database, it's what we call directory data in the book. And so it's basically a database, and you can partition and replicate it. But usually what people do is that they just replicate it because it doesn't change that much. So you can have a very simple way of replication. In some extreme case, if it changes rapidly and so on, you may, but all the techniques, you just consider it as a particular case of a distributed database. But now, and maybe I'm not going to go into the details, but if you have a lot of metadata, which is the case, for example, in what Marta has been doing with us in a provenance database, then the database can become big, and then you may go to more clever techniques. But
right.
And then it becomes really something powerful.
All right.
Okay. Okay, Patrick, we would have like 3 to 4 minutes before continuing. So if you want to have a break and take some water, okay. So
So I just mute my microphone.
Yep. Oi, pessoal, então mais 3, 4 minutos, que daria 1h15 de tutorial, era a nossa programação, para a gente manter o programa que o Sérgio nos pediu, né? E aí, no final, a gente vai ter também mais uns 10 minutos de Q&A. Então, vocês podem colocar perguntas, como a gente fez nessa fase, a segunda parte do tutorial. E se vocês acharem que a pergunta de vocês precisa ser respondida no momento, avisem, escrevam avisando, gostaria de fazê-la online agora, por exemplo. E aí eu combinei com o Patrick, se houvesse algum caso assim, a gente passaria, ele não se incomodou. Então, tem essa possibilidade também. A gente só não vai poder fazer muitos desses para não atrasar a programação, né? Mas uma ou outra a gente pode take online. Tá? Obrigado aí pela participação de todos. Uma pergunta do Amir. Amir, vou deixar sua pergunta para o final, tá bom?
Ainda não inventaram o cafezinho virtual, né, no Zoom, mas tudo bem. Fico devendo para o ano que vem.
Estou vendo aqui a pergunta, Cristina, eu te passo depois, tá? Ela pediu aqui o link para o Snowflake. Snowflake saiu, fez um IPO na Bolsa de Nova York de 1 bilhão, sei lá, uma coisa assim, de dólares, né? Então, foi uma coisa surpreendente. Eles estavam frequentemente, já há alguns anos, patrocinando o VLDB, eles estão pelo menos umas 5 últimas edições, eu me lembro deles como patrocinadores, e são um data warehouse, né? Compete um pouco com aquele da Redshift, eu acho, que é da AWS, não sei se é Redshift, é um nome parecido, assim. Isso, é. Uhum. Bom, a gente já deveria voltar agora. Vou esperar só o Patrick retornar. Redshift, é isso mesmo, Cristina. Curiosamente, Redshift é o nome que se dá da distância dos astros no céu, né? A distância que vem dos desvios da luz vermelha. É assim que eles calculam a distância dos astros. Esse termo, essa métrica é chamada Redshift. Talvez eles queiram se distanciar estelarmente, não sei o que é. Não sei qual é a relação com o Oracle. Eu conheço o termo da astronomia, eu não sei qual é a relação com dados, imagino que seja, pode ser contrário. Pode ser.
Fábio, vale fazer um comentário para quem está assistindo no YouTube. Tem mais de 40 no momento lá, que podem não entender português, só para avisar que estamos num break.
Okay, so sorry. So for those which are not Portuguese native speakers or even Portuguese speakers, we are having a very short break. Actually, Patrick is back. So I think we can pick up again and continue. Patrick, just let him set up. Patrick, I think we're ready to continue. If you're ready, just go ahead.
So let me share my screen.
Mm-hmm.
Okay, so now, so Fabio, how much time do I have?
I think 30 minutes would be fine, around 35 minutes.
No, I can, 30 minutes will be perfect. I will not go into the taxonomy, but the taxonomy is just a bunch of tables, so people will be able to look at. Okay, so now is a spotlight on new SQL. So hopefully I will answer in more detail the good questions we had in the previous session. So why do we have new SQL? So, well, basically, we need to combine, in fact, the advantages.
You're not sharing your screen.
Oh, I'm sorry. Let me go back to. Oh yeah, I forgot to push the button. So now I'm sharing. Now it's okay?
Yes, it's okay.
Sorry. So, so spotlight on new SQL. So, so as we just saw, NoSQL is on new SQL. NoSQL has this advantage of scalability using a shared nothing architecture. And also, I didn't go into the details, but they don't provide ACID transactions, so they relax strong consistency. And this is a way to provide performance, and they are very good with APIs for programmers, kind of lower level systems. And for relational systems, I would say the number one advantage is strong consistency. Transactions is very nice way for programmers to develop complex applications, right? They don't have to worry about the details. And standard SQL, which I think makes it very easy for tool vendors, companies like Business Objects, for example, and so on, which provide BI analytics to be portable on multiple platforms. So NewSQL is kind of a hybrid between NoSQL and relational. So basically, the idea will be to take the scalability and performance advantage of NoSQL with the consistency and transaction aspects. But there is more to the story. So as you all know, from the very beginning in database world, we had a separation between two basic workloads that companies have. you may have many other workloads, but these are the two basic workloads called OLTP, meaning that you have transactions on operational database, and OLAP, where you have analytical queries on the data warehouse, or in the case of big data today, a data lake. And typically the data which is in the OLAP database comes from the OLTP database. So you have tools like ETL or ELT, depending on how you do it, extract, transform, load, which do all kinds of things. And the problem is that in some cases, the cost of developing an architecture with ETL adds up to 75% of the analytical application. Okay, and but what's worse is that, well, of course, the advantage is that because you copy the data when you do queries, it's very fast, sure. But if you keep having updates in the OLTP database, well, the OLAP database is obsolete. Okay, so, and today there are use cases. I give you some example of use cases, but where you may end up missing business opportunities. So, for example, proximity marketing, that's one application we have been dealing with, real-time pricing, risk monitoring. All these applications need to do complex analytical queries on up-to-date data, not on data that might be, you know, a few minutes or a few hours late. So there's a new concept called HTAP, meaning hybrid transaction and analytical processing. It's a concept that you will find since 2015 around. And the idea is blending OLTP and OLAP workloads. So you basically have the OLTP and OLAP workloads on one single machine. Okay, so basically you do analytical queries on operational data. So of course the advantage is in terms of cost, no more ETL, so simpler architecture. In some cases, developing a new data warehouse takes like 3 years. And the main reason is because you need also to agree on the common schemas and so on. So the main objective is to do real-time analytics, you know, so meaning on current data. So I give you a few use cases. So this one, in fact, the terms new SQL comes from Google with the Spanner and maybe F1 application. And so the use case is Google AdWords. So you all know this application. This is the application that produces sponsored links as results of the search engine. So basically, when you do a search query, you will have the answer, but part of the answers will be paid by suppliers. And well, maybe it's not up to date, but at some point it was like $15 billion a year of revenue for Google, just this application. So this is with this application that suppliers can define the famous maximum cost per click, CPC bid, okay? So which is the amount of money they are willing to pay so that their ad is provided as an answer to a customer, to a user query. So basically the search engine works as an auction system. There's a competition between suppliers who want to get access to consumers, or really consumer models, which is the probability of responding to the ad, and they determine the right price offer, okay? So it's a very big database, and with lots of updates, because the updates are the fact that the suppliers, they have an interface where they can follow what's going on with their ads, and they can change their maximum CPC bid. So they keep changing it. These are updates, right? And this is hundreds of terabytes of data. Another use case, this is a use case we are working on right now at LeanScale. I mentioned LeanScale in a moment. It's network monitoring. And typically, the first implementation has been done in NoSQL. So typically, there's a NoSQL database to store data at high rates. So data is put in a data store, which is able to ingest data at very high rates. So the kind of data is network performance monitoring information about packets sniffed over the network. But the problem is that, so it's efficient to store the data, but the BI tools that cannot be used to access real-time data. So the data needs to be aggregated and exported periodically to an SQL database, which is used to query the data with the BI tool. So we go back to the separation between OLTP and OLAP. Another example, which could be useful here in Brazil, well, particularly in Rio de Janeiro, because you have Petrobras, is in oil and gas. So this is an example where you need to drill oil in a given location. And of course, the idea is you want to detect as soon as possible that the drilling prospection is going to fail. It's not doing anything useful, okay? And useless drilling costs a lot of money, of course. But how to do this? Well, you need to ingest real-time data from drillers. And in order to do this, you need transactions, because the transaction will guarantee that the data is ingested in a consistent way, okay? It's the same issue that you have in when you use event-based systems. You need to guarantee that what's put in the system is consistent. And also at the same time, you need to do real-time analytics of the data produced by the drillers. So again, we need to do transactions and real-time analytics on driller data at the same time. So there are many other use cases that I could talk about, but they all end up with this requirement, okay? Transactions and real-time analytics. In the case of the AdWord application, there's some real-time analytics, but it's really basic. It's what's done by each supplier. The transaction is more important. Whereas here, the real-time analytics is really critical because it's really part of the business. And what's happening today is that, so in 2015, Gartner talks about HTAP, but what's happening today is that we have a mix of HTAP and big data. So because you want to access more and more data from remote data sources. So the challenge is that you need to scale out transactions, so to have very high throughput, like millions of transactions per second. So by the way, just to challenge my colleague Amer, who will talk about blockchain, but this is not something you would do with a blockchain because the throughput is really bad. You want to do mixed OLTP OLAP workloads on big data. You want to do big data ingestion. So how do you get data from sensors or whatever, like the drillers? You know? You want to ingest data fast and query it with SQL. And in fact, the questions Marta had was really appropriate. You also want to have polystore capabilities because you may want to access all kinds of data sources, HDFS, NoSQL, and SQL here. So what are the techniques to do new SQL with HTAP capabilities? So basically, we borrow techniques from SQL and NoSQL. So from SQL, there are lots of techniques like parallel in-memory query processing, fault tolerance, failover, synchronous replication, which is the fastest, the best way to get real-time data, streaming. And from NoSQL, of course, key value storage and access, maybe JSON data, because the JSON is very popular document format, and also horizontal as well as vertical data partitioning. And this is typically called sharding in NoSQL. But that's not enough. It's not just enough to combine these two. So the big issues are, I think, scalable transaction management. And as you will, I will zoom on this part because it's, and the polyglot language and polystore. And I will also zoom on this part because these are the two parts that I know quite well. But in terms of parallel query processing, well, I guess, the technique from SQL, which can also deal with horizontal partitioning in the case of data warehousing, can be used. So what is the typical NoSQL architecture? Well, remember the NoSQL architecture. So it's like the NoSQL architecture in the sense that it's a share nothing architecture. And you have the different layers which can be implemented in some independent way, meaning on different nodes in a cluster machine. So it's very different than the architecture, the traditional parallel database architecture, say Oracle or Teradata. Because, for example, here, well, so this level is basically the same as in SQL architecture, except that in addition to SQL API, you may have a key value API. And you have two layers here, query engine, which is separated from transaction engine, and the key value store, which is, so basically, a NoSQL engine can be built on top of a key value store. In fact, when you look at the details later on Google Spanner or Linscale or whatever, they typically embark a key value store as the data storage layer, and they build on top of it, okay? So let me illustrate with one architecture, which I think quite interesting. So it's that of Linscale. So by the way, I am a scientific advisor for the Linscale startup. So it's another friendship story because the CEO and founder, you all know him, is Ricardo Jimenez Peris, who is used to be a professor at the University of Madrid. He's very well known for his contributions in transaction management, replication, snapshot isolation, famous Sigmod paper, etc. And so we are working together. And he's the transaction management expert. So the Linscale architecture is very interesting because the query engine, transaction management engine, and key value store, which is called Kiwi in the case of Linscale, they can scale out independently, okay? And this is very interesting because usually there is more constraints at this level, at the key value store level, because you have data. So you will not, you can replicate data, but you will not add easily more nodes. Whereas depending on the load, if you have more queries or more transactions, you may have more nodes to support those. So thinking in terms of independent layers, very, very interesting. Of course, you want to collocate, the query engine node with a transaction engine node with a key value store when executing some subset of transaction, for example, or a query. But it's just a side effect, okay? It doesn't need to be that way. Okay, so let me zoom on it will be probably the most technical part. I'm not really an expert, so this is really based on, it's not even a paper, it's a patent, so it's, but it reads like a paper, so it's easy. But that's a strong contribution by Ricardo. on a lean scale, on the way lean scale does scalable transaction processing. Here's a traditional approach, which is used by all systems, like all SQL systems, okay, is that even though they do a lot of parallel processing, at some point there is a single node bottleneck. Because at some point, part of the transaction processing is done on a one-per-one transaction basis. Like, for example, you will need to commit transaction or do locking or whatever, and there is to be a synchronization using lock tables or whatever, okay? So this is time, and basically, although the processing of the transactions has been done in parallel, to validate or to commit or whatever, there will be like a bottleneck, okay? In lean scale, and I will explain how it works later on, but the intuition is that, I guess you all know what it is, right? It's beautiful. So this is the waterfalls of Iguazu in Brazil. And this is really the way it works, you know? And so it's really parallel flowing of the water as opposed to here, okay? And basically what happens is that all the this is time, and these are the parallel transactions. So all the processing, all the commits and so on is done in parallel. But the difficulty is that because transactions are ACID, you need to provide a consistent view, okay? And this is what I will, I'm not sure I will succeed, but I will try to explain. And if you don't understand, you need to invite Ricardo for the next time. So here's a traditional approach. A centralized transaction manager. It has a component called central transaction management at a single node, okay? So basically, it performs whatever techniques for atomicity, committing, isolation, consistency, and durability. So isolation and consistency have to deal with concurrency control, okay? So we'll not talk about atomicity, which is not a big deal, but more about the fact that you have here the isolation. Well, most of the isolation writes and the isolation reads, and the durability. So the main idea is that all these ACID properties are scaled independently. They're scaled out independently using different techniques, but of course they can be combined. They can be composed together, okay? So how it works? Well, so all this is based on a technique that you will find in other, so you need a consistent view of the data, and it's called, there's an isolation level in SQL called snapshot isolation, okay? So snapshot isolation, for example, has been implemented in Oracle using versioning, what's the name? Multi-versioning of concurrency control. And so basically, what Oracle does and some other SQL systems do is that with snapshot isolations, they avoid read-write conflicts. Okay, so basically, if there is a write transaction and if another conflicting transaction want to read the same data, it will read a previous version. Okay. So with snapshot isolation, you end up to deal with only write conflicts. So basically, isolation rights have to be managed by conflict managers. You can have conflicts, but these are rare. It means that two different transactions, they want to update the same piece of data, okay? But of course, you need to isolate the reads, and to do this, I will explain how all this works together, but there is a snapshot server, and there is a commit sequencer, which will allow to commit transaction. For durability, you have loggers. So all these components, they can be implemented, local transaction managers, conflict managers, and so on. They can be implemented in a cluster, share nothing cluster, on different nodes. So let me go into the details. So the basic principles are to separate the commit from the visibility of committed data. This is really the key. I will explain with an example, but the way the transaction are committed is not necessarily the way the user sees the data. There may be some little delay to manage consistency. So we'll see that this is based on the management of commit timestamp, committing transaction, to detect and solve conflict before commit. So meaning that because transaction, because I'm sorry, all the conflicts are detected and resolved before commit, there is no bottleneck in committing transaction in parallel, which is really the major thing that needs to be achieved, okay? So let me illustrate this with the transactional life cycle. So when a transaction starts, it needs to have a consistent view of the data. It's provided by a snapshot server, okay? It's like this camera that takes a picture of the data, okay? And very important, the transaction gets a start timestamp, okay? So all the timestamps are synchronized, okay? And then there is a local transaction manager, which gets a start timestamp from the snapshot server, okay? So the transaction will read the state as of start timestamp, and the write-write conflicts are detected by the conflict manager on the fly, okay? And what's this? And then at commit, the local transaction manager needs to orchestrate the commit. And this is how it is done. It is done in here the life cycle. Okay, so it gets a commit timestamp. So the local transaction manager for that particular transaction only knows the start timestamp, which was given by the snapshot server. So now it gets the commit timestamp, and in fact, it needs to synchronize this with the initial timestamp. So there's some logging. So in order to do undo redo, so basically it's using the WAL protocol. So this is logging the write set, making the updates public, so integrating the data in the write set and reporting the commit timestamp, okay, to the snapshot server, so that the snapshot server will know that there's a new version of the data and will be able to deliver that data. So let me illustrate with this example. So let's assume that the snapshot server, because all this is controlled by the snapshot server, it gets this sequence of timestamps. These are commit timestamps. So things need to be ordered by commit timestamps. So for example, it gets 11, then 15, then 12, then 14, then 13. So what the snapshot server will do is that it will let's assume that it starts at 10. It will, so 11 is the next timestamp, +1, so it's going to be okay. But when it gets updates for timestamp 15, it will not do anything. It will keep timestamp 11. So basically, if there are transactions that request a timestamp from the server, they will get 11. They will not get 15. And why is that? Well, it's because, as you can see here, you may have 12 or even 13 or whatever. So you may have other timestamps that come later. So when it gets 12, then it can move because there's no gap, okay? And when it gets 14, it will keep 12 because there's a gap, okay? And only when it gets 13, it will move up to 15, which is, so basically it will provide a sequence of snapshot of timestamps with no gap. And so this is the consistent view that is provided to the transactions. And this is the commit order, which is different, of course, okay? So this is really clever. And this provides, of course, because it has very strong scalability. So this is using multi-row transactions. Each transaction manipulates 2 rows. So it's very basic, but it shows linear scalability, okay? Up to 2 million transactions per second, okay? With increasing the number of cores in cluster architecture.
Patrick, maybe we're getting to the...
Yeah, so a few minutes, and I'll just say a few words. So the other major innovation is related to Polystore. So I mentioned Polystore. So the Lean-Scale integrates the Polystore architecture that was done in our joint project. It was a European project. So basically, there's a data lake API here. It's called data lake API, which allows the query engine to directly access the partitions, the data shards, okay? So this is very important for parallel Polystore query processing. All the Polystore system, when they do query processing on big data, they have a bottleneck because the data is integrated by single nodes. Well, here we do it in using multiple nodes, okay? So basically we use traditional parallel algorithm, but we exploit sharding, okay, with polyglot capabilities and so on. So this is a paper that was published at the Big Data Conference. And there's a revision of an extended version for the DAPD journal. So just to give you an example, this is a query on Lean-Scale and MongoDB. So this is the data in relational new SQL format in the key value data store. And these are Mongo shards. And this query, which has been partitioned by the query engine, is able to directly access the partitions. So there is no integration, centralized integration of the shards. Okay, so that's a contribution of the paper, and it's a very important one. Okay, so what you will see by yourself is the taxonomy of new SQL. So basically comparing new SQL with NoSQL with new SQL on the different dimensions. So I'm not going to go into this, but it's very interesting, but it's easy to read. In fact, you have comparisons of different systems like Spanner, Lean-Scale, SAP HANA, which is an in-memory column store, MemSQL. So all these do HTAP. There is also a splice machine, which is a very interesting system. Okay, so I don't go into the details because I would like just to go to the conclusion so that you can have questions. So new SQL is a very hot topic. It's definitely very important because you can combine, you know, the two different workloads, OLTP and OLAP. So the current strength is that, well, it's fast growing in terms of CAGR, which means compound annual growth rate in terms of market. So that's a business thing. So you are maybe more interested in research. So in research, there's all this polyglot SQL. So for example, there's a very interesting SQL ++ extension, I think it was done at University of San Diego. It's an extension of SQL which is compatible with document databases, and it's being used right now by some document databases. Of course, there are a lot of issues on Polystore query processing. So, for example, there's a SIGMOD paper by Ioana Manolescu's group this year on materialized views. So, materialized views is definitely an important topic. At Linscale, we find very important to combine streaming and complex event processing with new SQL. Something that we do in our joint project with Fabio, Marta, and so on is to deal with scientific applications. So, for example, an issue would be new SQL HTAP with scientific workflows. Of course, machine learning and analytics. So you want to have this combined with the Hadoop or Spark software stack. And we also need benchmarking. Okay, that's the last slide. So I'm going to quit this, and I'm going to stop sharing.
So thank you very much, Patrick. It's very interesting talk,
Just in time.
A very hot topic. And as a result, we have few questions here. Maybe we should first take a picture, Sergio. What do you think? Before people leave, how do you want to do that? Do you want to take it, or how are you doing it?
You are the chair.
Okay, so I can take it. So just if you want to turn on your cameras, videos,
people, at least maybe not microphone because it will be complicated, but
turn on your videos. So I have to take a few shots. Okay, so still waiting for a few. Vanessa Ribeiro, so the ones that can turn on, so please do it.
Yeah, I can see familiar faces, like I can see Danielle.
So I will take this one now. Smile, say she's. Yes. Now one more. And there is a third frame. Yeah, so I capture everyone. Thank you very much. Then I will send it to the coordinator to put it on the web page. So let's go to the questions. So the first question actually goes back to the beginning of the second part of the talk by Amir Khatib. So I will unmute Amir if you want to turn on your video and directly ask the question to Patrick. See if I can do that. Yes. Oops. No. Where is Amir? Okay, Amir.
Yeah, Amir is here.
Yeah, I'm trying to unmute his.
But he's asking for the microphone.
Yes, okay, so now he's on. So
you're
please,
on.
go ahead.
Hi, Amir.
Hi, Patrick. Okay, thank you for your nice presentation. Just a quick question, please. I'm caring a little more about the industrial part. You showed the two main players, the Google Big Table and the Amazon Dynamic DB at the first part of your presentation. I would like if you could compare the performance of these two systems, because you showed that one used the tabular format and the other one uses the key value type. I would like to ask you to elaborate on this if you can.
So your question is comparing key value versus big table, kind of tabular format. In fact, it's a big discussion we always have with my colleague Ricardo, because in fact, tabular, so in the book, we have this classification, key value versus tabular. Whereas Ricardo would say they are all key value, and he's right. So you can, and this will answer your question, because in terms of implementation, it means it's really the same thing. They use, although DynamoDB uses a peer-to-peer implementation, Cassandra uses a combination of DynamoDB and Bigtable, and HBase and Bigtable are the same. So the bottom line is are all key value, and the main reason for key value is you don't need a schema. And so basically you can put whatever you want into the value. So in DynamoDB, you can have columns, and in Bigtable, the same. So there's nothing, now you can compare the performance, but I cannot answer because I didn't do it. And there's no benchmarks, standard benchmark like in the databases. But there's no reason that the performance should be different because they all exploit the same hardware capabilities. So, so basically, they are all very scalable. DynamoDB is very interesting because they use, I don't know if you know, they use a distributed hash table concept called consistent hashing. But it doesn't really bring performance, it just makes updates easier. So when you have to move data, it only affects the neighbor nodes. So, but now in terms of performance for new SQL, I can tell you the story, but I don't think it's a secret. But the first version of so Spanner has been built on top of, well, using Bigtable technology. And Linscale was, the first version was built on top of HBase, which is the open source version of Bigtable. And it had some limitation. So it's very good if you just do key value access, but if you want to do more, it's not intelligent enough. So the KV store that we have in Linscale is much, much more efficient. In fact, we push functionality inside the KV data store. The last one being semi-joins. So you all know about bind joins and all these good techniques. So we can, so there are a lot of issues when you move to new SQL about this new SQL system. If you just keep this new SQL system to do whatever they have been designed for, they are fine. Okay, sorry, so it's a long answer.
Yes, thank you, Patrick. So thank you, Amir. So now there is a question I take from Veronica Santos. Veronica, if you can turn on your video, if you want to ask it online, then I can unmute you. Otherwise, I can ask the question. It depends on whether you feel comfortable or not. Okay, so maybe I just ask the questions that Veronica wrote. Okay.
Yeah, I see the question.
Can you see it? Okay, yeah. So go ahead. So there is a kind of common sense to say that schemaless, you can read it, right?
Well, it's a very good question, actually. So maybe I'll read the question is that when is it an advantage? Well, schemaless is an advantage of NoSQL. Schemaful is an advantage of relational. So how can applications benefit from it? So the bottom line is that if the data is structured and if you discover the schema, you can do a lot with the schema. You can do query optimization, well, all the stuff that Fabio and Sergio and all the people here know very well. But if you know nothing about the data, well, schemaless is the way to go. So my view is that, and this is what's nice in new SQL. New SQL allows you to achieve a trade-off. So if you don't know anything about the data, you will be like schemaless, okay? And for example, in Linscale, we plan to support JSON data. So JSON is like XML, so you have some little structured information. But if you do have information, then you can have a schema. In fact, in Spark SQL, it's the same thing. You can have a Spark SQL, you can have something called RDD schemas. So schemas are very important. Schemaless is an advantage if you know nothing, because at least you can get to the data. But so I think NewSQL is very interesting, but Spark SQL is also something very interesting in that direction. Okay, and the way it gets very interesting for applications is that when they have relational data, for example, so structured data, but some part of the data is unstructured. Okay, so in relational databases, you can have JSON or XML columns, and this is where you would put the parts. So it's really ad hoc. You can do better than that. Okay.
Okay, Patrick. So there is a question by Cristina Ciferi from USP, and she's asking about if you can correlate HTAP with data lakes. How do they? Cristina, if you want to add something to your question, feel free, please. I have to unmute you. Oops. Yes.
Okay, thank you. I know that data lake stores raw data, but in fact, in practice, there is some translation to formats like JSON and so on to be used in practice. So my question is, the hybrid approach is like a data lake, but located together with the operational databases. I guess a little more well-designed, but is a kind of similar concept.
So basically the concepts HTAP, data lake, data warehouse, and so on, they are all orthogonal, but they do converge at some point. So for example, so it really depends on what the customers want to do. So you all know that a data lake is like a data warehouse, but it doesn't have schemas. So it has schema on read. And so basically, well, to make it simple, you store everything in HDFS, and then when you access the data, you can extract and put it in some other more structured forms. And as you mentioned, a document database is a good way. So I would position, in the book, we position data lake as in the big data chapter as opposed to data warehouse. Although in industry it's very complicated, because now the big data warehousing players allow, like Oracle or Microsoft, allow you to access HDFS data using, it's called external tables. And the data lake players, like Hadoop companies and so on, they allow you to access, of course, HDFS and combine with relational data. So they all play that game. So now the question is different, is that once the data is in the data lake or in the data warehouse, do you need to do updates? And so usually no, okay? So it's read only. So my feeling is that it's orthogonal to HTAP, and an HTAP system will allow you to, for some application where you want to do analytical queries on up-to-date data, you will do this on the operational data, but you may also at the same time take that data and put it in a data lake for other purposes. So, and there are some applications we are exploring right now with potential customers where they have data warehouses, data lakes, and so on. So the situation is more complicated. But one thing I've noticed, in fact, I was teaching distributed architectures a couple of weeks ago and to a big company, and they have a data warehouse, and typically they have inconsistency because the data warehouse gets data, historical data, and what happens is that the historical data has different business rules. The business rules, they change, okay? So they would like to have consistent queries, And in order to do this, you may have to do updates directly. So the situation is not that clear. You know, for some applications, you will need a data warehouse or data lake, but HTAP will be complementary. Okay.
Okay, I see. Thank you.
Thank you, Christina. So we would have we'll take a last one. We're already over time. But then there is a question by Eduardo Almeida from Federal do Paraná. Patrick knows well.
Yeah, and, I remember Eduardo.
So he's asking if you know whether someone is using data vault modeling in data lake. It continues in the data lake context. So he's referring to a data vault modeling. And he continues saying, because telecom companies in Brazil are using such modeling, they can inject 1 billion tuples per day. So he's arguing that that model would allow the ingestion of 1 billion tuples per day by using the data vault modeling in data lakes. I don't know that, but maybe Patrick.
No, well, I don't know this modeling. I know data vault, but I don't know how they use it for modeling in data lake. So that might be interesting. Well,
I don't know whether Eduardo is here. Are you here, Eduardo? Maybe.
So he has a question and left.
I don't know. I can't see him.
So maybe he's been disconnected. But we can. Yeah. But it's a very interesting question because. Of course, telecom companies, and I was mentioning an example, you need to inject lots of tuples
yes.
per day or even per
yes.
second.
Yes.
So that's really an issue. But if you put in a data lake, then the issue is that how do you do on-the-fly queries, right? Yep. So this is where typically a product like an HTAP product, like Linscale, will allow to do analytical query at the same time that you do the transaction, which makes the ingestion consistent. So whereas here, well, basically it's like a data warehouse. You have to wait that the injection has been finished, and then you can start doing the queries. Okay. Whereas with Linscale, you can do it on the fly. So and that would make a very big difference in terms of capabilities. Okay.
So I think it's time for us to wrap up. I'd like to thank Patrick very much for this very didactic tutorial on NewSQL, NoSQL, and as always, very interesting talks, and very nice to have you here within the Brazilian community. Maybe Sergio want to say a few words before we wrap up the session. Please, Sergio, as the local coordinator.
Just again to thank you, Patrick, for your nice presentation. Very nice talk. I think I've seen all the messages people really appreciated. You can see also the YouTube movie after. Everybody else, whoever wants to watch it again. And thanks again for accepting to present this tutorial. Thank you very much.
And I take profit from the moment to invite all of you. Have a keynote by Tim Kraska, including Patrick, if the time allows, at 1:30 today, later on in 2 hours, kind of 2 hours, 2 hours and a half. Okay, thank you very much.
Thank you, everybody.
Bye-bye. Stay safe. Bye-bye.
Thank you.